Okay, so we should be recording at this point. So I'm going to have the worksheet, and then I will obviously be going back and forth to the whiteboard because there's a lot of material that needs to be written out as we're working our way through this here. So the first question is a redox reaction, and we are going to balance the redox reaction in basic media. So it is important when we're doing this, you want to pay attention to the actual wording in the problem, because that's going to tell you whether your final answer needs to be an acidic solution or basic solution. It should always tell you. If for some reason it doesn't, you can go ahead and assume that it would be acidic, but it's usually going to tell you in the problem. All right, so there's a couple things we need to do here. We need to provide the half reaction for the oxidation, the half reaction for the reduction, and then we want the net reaction. That really shouldn't say provide the net balanced half reaction. It should be the net balanced reaction, or the net balanced redox reaction. All right, so in order to approach this, the first thing we want to do is break down the oxidation and the reduction. So the half reactions are going to be ClO2 aqueous, and that is going to go to ClO2 minus aqueous. Okay, and then the other one is going to have a bit more balancing to it, and then we'll come back and look at electrons. So we have peroxide, aqueous, and then that is going to go to the O2 gas. Now, when we take a look at this, we have a balancing problem with the hydrogens. So the way that we balance hydrogens, if the oxygens are already set, is we want to balance using acidic protons. So I'm just going to throw 2 additional acidic protons. Now, I want to mention 2 things. The first one is, you can see that acidic protons do not always have to be placed on the left-hand side. So when we were originally working in class and showing examples, they by chance always ended up balancing on the left side, but that's not always required. You can also put them on the product side. You can use acidic protons or water wherever you would like for balancing. Okay, so that's the first thing. The second thing I want to mention is, when we get ready to start balancing these, you have acidic protons for balancing hydrogens, and water is used for balancing oxygens. So there was a bit of confusion on Tuesday. Some of the groups were asking me, do we add water in order to balance hydrogens? The answer there is no. Water is not optimal for balancing hydrogens, because H2O means that anytime you use a molecule of water, it has to come with an even number of hydrogens, and you may want an odd number at some point. So that's why H plus is optimal for hydrogen, because H plus is simply 1 hydrogen. You can balance as many as you would like. And then H2O is mono on the oxygen. So then you can throw as many waters as you'd like. And that's why they're each respectively optimal for those individual elements. All right, now, because this is in basic medium, I'm going to have to cancel this out with the hydroxide. So I'm going to need 2 hydroxides in order to balance this out. Okay. Now, what I do to the left, I'm going to have to do to the right. So I'll have 2 hydroxides there as well. And now I can start taking a look at the electrons. So keep in mind that I'm going to put these together. That's going to create 2 waters. Okay. Excuse me one moment. Noah, I need you to be quiet. I'm teaching class right now. I need you to keep it quiet, please. Okay. So that's going to be 2 waters. I'm sorry about that. And then if we take a look here, I've got the hydroxides on the other side. So now for the electrons. If you take a look at the electrons that are being passed back and forth, in the top situation, we've gone from neutral to negative. So that means an additional electron has been added. Okay. Now, if we come to the bottom, I have 2 electrons on the right, if you look at the balancing. And that's because the 2 hydroxides are going to lead to a 2 negative net charge on the products, on the reactant side. And then on the product side, I've got O2 gas and the water, and those are both neutral. All right. So that means I'm going to need to do a ×2 distribution up here. And then I can turn around and I can condense all of this together. And I say 2 ClO2 aqueous. Now remember, the electrons are going to cancel, plus 2 peroxides aqueous plus 2 hydroxides aqueous is going to yield the oxygen gas plus 2 water molecules. Those are a result of the acid-base neutralization there. Okay. And then finally, I also will have 2 Cl, 2 did not come out well, 2 ClO2 minus. Okay, so, and that would be aqueous. That is the net reaction that we would have there. All right, I'm going to pause here. Are there any questions regarding this overall reaction? So we broke it down into half reactions. We balanced the elements, we balanced the electrons, and then we bring it all into a net reaction. Okay, good. So again, the only change if this was acidic is that I wouldn't do that hydroxide balancing. And you always want to double check your final equation, because your final equation will let you know whether you're in hydroxide or acidic medium. And you have to make sure that you're mirroring whatever the question was asking. All right, so moving along here, for number 2, you need to sketch a voltaic cell for the following redox reaction. So we've got silver and lead that are interacting with one another here. And it asks you to include multiple things. So we're going to set it up as 2 half cells in the beakers with the respective electrodes, so the solid metal plates. We're going to have a connecting wire that's hooked up to a voltage meter, a salt bridge, and then we're going to label where the anode and cathode are, as well as the general electron flow. So let's go ahead and take a look at that. Okay, so we're on to number 2 now. For this problem, you can get started. And by the way, for people that haven't started homework yet, I would suggest that you get started on that soon. Many of the problems in there are going to be similar to this. All right. So here is our first half cell, and we'll draw our second half cell. Okay, we need the metal electrodes that are going to be placed into these individual half cells. Okay, and you can label these. So we need to determine what's going on where. If you take a look at the reaction there, you'll see that the lead is going to come over to the anode. So I'll just label PB there on my metal electrode. And in solution, I'm generating PB2+ according to the reaction that was there. Okay, and I'll put this in some sort of aqueous medium. It could be lead sulfate or lead nitrate. It doesn't really matter what the salt is, but we need a source of lead 2+. So then I've got silver hanging out at the cathode. Again, I need to have in solution the generation of silver plus. All right. I need to make sure that I add a salt bridge that's going to connect the two. Again, doesn't really matter what salt you pick out. You could have potassium chloride, like our previous example, sodium chloride, but you need some sort of salt bridge that's present. And that's in order to help with the charge buildup. All right, and we need to connect the electrodes through a general wire. And you don't need to get fancy at all. You can just write V or volt up here, right? This will be our voltage meter that we connect to the electrodes. And I'll go ahead and label down here, we mentioned a moment ago, this is our anode, and this is our cathode. And then the general electron flow in this situation is going to be going this way. All right, so the electrons are coming from the anode, flowing towards the cathode. This is what we went over in class when we were drawing rough cells like this. And this would be an acceptable answer for a problem like this, where you're asked to sketch a very general setup. Right? Now you should also be, this question did not ask for it, but you should also be comfortable with the common notation, which is where we're doing the single breaks and the double breaks, where you need to look at the states. So you could have PB solid, single break, PB2 plus aqueous, and if it's standard, you can put 1 molarity. Then double break for the salt bridge, the Ag plus, single break, and then the Ag solid. All right, so be comfortable writing both ways. That's obviously an abbreviated way. This was asking for you to sketch and show what the actual crude cell would look like if we set it up. And that leads directly into problem 3. All right, so problem 3 here states that it wants you to calculate the standard cell potential for the sketched voltaic cell in problem 2. So all we need to do is take those values. You would go into your reduction potentials in your table and you would find the values there. So for number 3, the standardized E cell for this is going to be the E cell of the cathode. The cathode is silver in this case. So you grab that value off the chart and it should be 0.80 volts minus the potential for the anode. And the anode in this case, if you go to the table, should be negative 0.13 volts. And so if you put those together, you're going to get 0.93 volts, right? And so just as a reminder, this is the silver cathode value, okay? And then this is the lead anode value. All right, I'm going to pause here because we just tackled 2 questions. So are there any questions leading up to this point here, whether it's about the sketched voltaic cell or how to calculate a standard potential? Everyone still comfortable? All right, so if that's the case, let's go ahead and take a look at number 4. So number 4 says use the standard E cell. So we're doing the same thing we just did in the previous problem for the following reaction to calculate the delta G and the equilibrium constant for the redox. All right, so there's a couple of ways that you could approach this because there's multiple equations that tie in together. So the way that I'm going to approach this is I'm going to calculate delta G after I find the E cell. And once I have delta G, I'm going to tie that back into the equilibrium constant. So there are other ways that you can represent E cell to the equilibrium constant, but this is the process that I originally intended for the problem to be solved with. As long as you're getting to that answer that you need, then you should be fine. All right. So in order to start, I want to know what's oxidized and reduced, meaning I want to know what's going to be at the anode and the cathode, because that's important when I'm determining how I set up the E cell. So you don't necessarily have to do entire half reactions, but if you take a look, you're going to see that the chlorine, if you're looking at charge and keeping track of electron transfer, the chlorine in this case is going to be oxidized, which means I'm going to associate it with my anode. And the bromine in this case is going to be reduced. And so I would associate that with my cathode. Now, if you go and you find these values, you're going to find that the standardized value for the chlorine would be 1.36 volts. And the standardized value for the cathode here for bromine would be 1.09 volts. So in order to get the E cell, I simply have to put that together in my regular cell potential equation. So standardized E cell is going to be the cathode, 1.09 volts, minus plus 1.36 volts. So that's just going to turn out to be a minus when I calculate that. So you put that together and you end up with negative 0.27 volts, right? Now the question did not ask this. However, there have been questions previously that have asked, is this a spontaneous reaction? So you could determine that from delta G. You could also determine that from your E cell. So at this point, you could make a determination and the answer would be no, because it's a negative voltage in the way that it's set up. So in order for a redox reaction to be spontaneous in generating electrical current, you cannot have a negative voltage for the cell potential. It's going to need to be in the positive region. So what that also means is that from a predictive standpoint, if we know that this is not going to be a spontaneous redox reaction, we therefore can predict that delta G should be positive. We're not going to expect a negative free energy in this case. All right, so speaking of that, we want to turn around and calculate the delta G now that we have E cell. So delta G standardized for this reaction is going to be equal to, now I need to know what small n is, meaning the moles of electrons transferred. So if you come back and you bring this reaction up, you can see the balanced reaction. You have 2 bromine as elemental bromine becoming 2 Br minus, and you have 2 Cl minus becoming a single Cl2. So if you were to write this out, okay, and probably most people can gather it just from looking at it, there's going to be 2 electrons that are being passed back and forth between this redox setup. So that means that when I get ready to do my negative N value here, it's going to be negative 2 moles of electrons. Right? I then need Faraday's constant in order to make this work. So the Faraday constant, generally rounded, is going to be accepted at 96,500, and that's coulombs per every 1 mole of electron. So I now have gotten rid of moles of electron unit-wise, and I'm over to coulombs. Okay, and then times the negative 0.27 volts. Okay, now if you break down volts, the coulombs are going to cancel, and you're going to end up with the joules. So when we put all of this together and you solve for delta G, you're going to find that this equals 5.2 times 10 to the 4th joules. Okay, so you can also write that, since delta G is typically kept in kilojoules, we can also state that this is 52 kilojoules. Again, just to double check on ourselves, this is a positive value, which is exactly what I was expecting since I had a negative cell potential. This is all lining up for a non-spontaneous reaction that makes sense. All right, so now we need to calculate the equilibrium constant. So the way that I'm going to go about this is I will say, now that I know that, I can also state that delta G is equal to negative RT, which is the gas constant in its joules form, as well as the temperature, okay, is equal to RT ln of K. This is big K, all right? Don't get confused because we now have a little k that we're referring to when we start talking about rate constant laws. So in order to solve this, I'm going to need to algebraically rearrange and get K by itself. So that would mean that I could divide through by negative RT to get negative delta G over RT, and that leaves just the ln of K. So how do I get just K? I'm going to need to take the anti-natural log, which is the mathematical value E, and I need to raise it to the value that I'm solving for there. Okay, so to put that into mathematical terms, when I rearrange this, what I'm looking at is K, the equilibrium constant, will be equal to E, and that E is going to be equal to negative delta G of the reaction over R. Sorry, this is small writing because it's supposed to be exponential there, over RT. Right? So what I'm going to do in order to help write this out so you can clearly see the values going in here is I'm going to write this large, and then I'm going to put a very big E here because it goes up exponentially. All right, so let's first set up what this exponential term would look like. So we're going to want to keep it in joules, not kilojoules. And the reason for that is that the R value contains joules. So we need to have canceling of values when we set this up. Okay. So the delta G in joules was 5.2 times 10 to the 4th. So I'll go ahead and I'll start with that. I'll say negative 5.2 times 10 to the 4th joules. That's the numerator. Over, okay, now the R value, don't get confused with the 0.0821 that we use when we're doing gas laws. This is the same R, but there's different units. It's not the atmosphere liter per mole Kelvin. This is going to be joules per Kelvin mole. And because of that, we get a different value. So R's value is going to be 8.314, and the unit there is joules over Kelvin mole. All right. And then the temperature here, even though it's not given in the problem, is assumed because we're operating under standard conditions. We did a standard E cell, we did a standard Gibbs free energy. So we're talking about standard conditions. Therefore, 25 degrees Celsius to Kelvin is going to be 298. Okay, or 298.15 if you're getting specific. Okay, so this is the exponential value. So now what I was talking about, this is really E. Okay, so E is going to be raised to this entire mess right here. So you'd probably want to solve it and then raise E to that. So if you work all of that out on your calculator, you should end up with E is going to be raised to the negative 20.998. And that is going to equal, keeping sig figs in mind, you only get 2 because the delta G had 2, and that's what's being input. Okay, the rest of this is constant material or assumed exactly 25 for the temperature. So you end up with 7.8 times 10 to the negative 10th. This is unitless because this is equal to an equilibrium constant. Equilibrium constants do not have units. Okay, so let's take a pause here because there was a lot of math involved in that problem. So does anybody have questions regarding problem 4, whether it's how we calculated cell potential, how that can be related to delta G, or how delta G can be related to the equilibrium constant? Okay, perfect. We're flying through it. So if we are good with that, I'm actually, because I'll start running out of space soon, I'm going to come back and start deleting some of what's on the top here. Again, this is all being recorded and will be posted early this afternoon. So don't worry if I'm deleting something you haven't caught up with. You'll be able to go through on YouTube and rewatch this, pause it, all that good stuff. All right, so the next one then is number 5. And number 5 was taking a look at the Nernst equation. So the Nernst equation is going to be utilized when we no longer have standard conditions. So the first part of this problem has you calculate the standard conditions for the cell potential, and that's required for the Nernst equation. It's a prerequisite as we're moving towards it. All right, so what we have here is iron 3+ is going to iron solid, so it had to gain electrons. And the magnesium is going from solid to magnesium 2+, so it was the one oxidized because it lost electrons. So magnesium is oxidized here, the iron is reduced. So we're going to set up our standard E cell like we've been doing. That'll answer A, and then the next thing we're going to do is head over to B with those concentrations. All right. So the first thing that I would do is I would say, what is the E value for the magnesium? And again, just as a reminder, the magnesium was oxidized, so that's going to be the anode here. Okay. And if you look at this, the magnesium was negative 2.37. Okay. And the other one, I think this is where the issue came in. One of my groups pointed out, our chart in OpenStax did not actually have this for the cathode. So you would have had to go search another table somewhere posted on the internet or in a different book. Okay, so the cathode value for the iron reduction was negative 0.036 volts. Okay, so if we have that, then we can calculate the standard cell potential. So we're going to go with E cell. Cathode first is going to be negative 0.036 volts. And then that will be minus a minus. So now we're adding 2.37 volts. Okay, so that means that the E cell potential net is going to be a positive 2.33 volts. So that's the answer to A, the standard cell potential. Now, in order to use the Nernst equation, we're going to need that value, and we can set it equal to the gas constant summarized over N, and then the natural logarithm of the concentration for the equilibrium constant, right? So if we come over here, the way that we're going to solve B is we're going to say E cell, And note that there's not going to be a standardized value here because we're moving out of standard conditions, is going to be standard E cell, 2.33 volts, minus 0.0257 volts over N. Now we have to determine what N is in this case. So if you bring this back up, you can work out the half reactions, or you can take a general look, all right? So if I take a general look at this balanced reaction right here, I can see, let's use the iron for example, right? I've got iron 3+ going to iron solid. So that's a transfer of 3 electrons. There's a stoichiometric coefficient of 2, so it's doing it 2 times. That's a total of 6 electrons. I got to make sure the same thing is true for the magnesium, and if it is, that's the number for N. If it's not, I have to find the common factor. So magnesium, there's 3 of them that are neutral, and then they go to 3 of them at 2+. So 3 times 2+ is 6+, so there's a loss of 6 electrons. So magnesium is losing 6 electrons, and iron is gaining 6 electrons in this case. So N is going to be equal to 6. Okay, so that's the value that I'm going to put down here. And then I have the natural logarithm, okay, of, now it's the product over the reactant. So in this case, if I go back and I look, it's only for the aqueous because solids don't participate in equilibrium values. And I've got magnesium as the product. Okay, so magnesium right here is highlighted at 2.50 molarity. And I've got the iron as the reactant, so that'll go in the denominator. That is valued at 0.001 molarity. So let's go ahead and plug those values in here. So it will be ln of 2.50. Now this can be where people get tripped up. It's cubed, because I still have to realize I'm writing an equilibrium constant here. There are stoichiometric coefficients floating around in this equation. I have to pay attention to those or I'm not going to get the correct value. Right? Now, same thing is true for the bottom. So I'm going to put 0.0010 squared. And if you solve for that and take the natural logarithm, okay, and put it all together, then you'll end up with E cell is equal to 2.26 volts. All right. So at standard conditions where everything is 1 molarity, the voltage is 2.33. And when we deviate here at those given concentrations that were provided, the E cell is 2.26 volts. Right? The biggest problem I saw was people were forgetting that we're operating in equilibrium here. And if you forget that you're operating in equilibrium and you just throw in 2.5 and 0.001, then you're going to have issues when you're attempting to solve this. All right, let's pause here before we head over. This is the last of the electrochemistry problems that we practice. Is there any question here?
Can you explain why it's cubed and squared in the natural log?
Yes, so if you're taking a look at this, it's the natural log of the equilibrium constant, because it's got the products over the reactants here. Now, again, it's only for aqueous based. So what it's saying is, let's take the log of the, which one was it? The iron, right? Yeah, no, the magnesium was the product. So the magnesium two plus over the iron 3+. So when we're looking at that, we have to consider the stoichiometric coefficients. If you look at this equation, the stoichiometric coefficient for the magnesium 2+ is 3, and the stoichiometric coefficient for the iron 3+ is 2. So those stoichiometric coefficients, 3 and 2, are going to be what I am raising this value to. So that's why this is 3 and 2. Does that make sense?
Yes, thank you.
Not a problem. All right, so if there's no other questions on that, then we will go ahead and we will start moving over to the kinetic problems that we're going to take a look at.
I had a question real quick.
Sure, go ahead.
Where did the 0.0257 volts come from?
Okay, so that value is a constant value, and it comes from the Nernst equation itself. So the Nernst equation has temperature, and it also has the gas constant R built into it. So when you're operating at a standard value, you're going to have 0.0257 volts, okay? And that is just simply the 8.134 value for R and a given temperature. So in this case, we're saying the molarity changes, but we weren't provided with a temperature, so we assume that it's staying the same. And that's just those values put together. If you have two constants and you know what their values are, it's taking an additional step of multiplication out of the Nernst equation for you.
Okay.
Does that make sense?
Yeah, thank you.
Sure, not a problem. So let me pause one more second before I jump on, because I know there was a lot with this question. Are there any other questions before I move on? Please feel free to speak up. I'm happy to explain more. Okay, take your time in your homework when you're doing it for people that haven't done it yet. There is another problem like this in your homework. So you'll get another opportunity to attempt to work through something like this. All right, so if that's the case, then we will go ahead and move to 6. Okay, so 6 says, consider the following reaction. We're now moving and shifting over to kinetics. So we've got the N2O gas going to the molecular nitrogen and the molecular oxygen. And there's 3 different things that are being asked here. The first one says, express the rate of this reaction in terms of change for each reactant and product. So that's where we're saying the change in this reactant is equal to the gain in this product, which is equal to the gain in this product. We set all of that up, so that'll be the first step. In B, we're going to actually start calculating a rate. So it says in the first 15 seconds, so that's time 0 to time 15, there was 0.015 moles of oxygen produced in 0.500 liters. That means we need to put that together to get a molarity, right? What will be the average rate of the reaction during this time interval? So that's what we'll do there. And then C says, what would be the change in the reactant concentration over that same time period? So what we're going to do is find the value for B, and then because we equate all of the values to one another in A, we can set up the relationship and we can solve for the reactant concentration in C. So that's how we're going to approach this. Okay, so the first step is let's set this reaction equal to all the reactants and products so that we have that working relationship. So this is part A of 6. That looks like that's crossed out there. All right, A. So -1/2, because it's negative due to the reactants disappearing, and it's 1/2 because the stoichiometric coefficient was 2, is going to be multiplied by the change in concentration of the N2O over some given change in time. And that is the same as saying that we can set this equal to 1/2 the change of nitrogen gas in some change time, which is the same thing as saying the change in oxygen gas concentration over the change in time. All right, so just to be clear, we're going to look at 1, 2, and 3. Okay, here's 1, this one is 2, and this one is 3. I'm just arbitrarily labeling these with numbers. Number 1 is negative because it's a reactant. Reactants disappear. Number 2 and number 3 are positive because they're products. They are appearing. The sign is only telling us the direction in which the rate is going. Okay. Number 1 has a 1/2 and number 2 has a 1/2 because when I look at this, the balancing here has 2's, right? Now it's important that you remember this is the way these values are treated in kinetics. We just came from putting them up as exponential values when we were dealing with equilibrium constants. Now they're being pulled down and used as fractions. So that's where those half values are coming from. It's 1/2. If there was a 3 in front of here, it would be 1/3. If there was a 4 in front of here, it would be 1/4, etc. And there's an implied 1 in front of the oxygen. So that means I don't need to put anything. because it would just be 1 over 1, which is 1 there. So that's how all of these are set up equal to one another. So then in B, we're given the time and we're given a concentration, right? So there's a couple things we want to consider here. We're starting off at an initial time with 0 concentration of oxygen gas, okay? And the time is also going to be 0, the initial time. Now, the final time is going to be 15 seconds. So if I look at that, the net time then will be 15 seconds. And the net concentration change is going to be whatever the concentration is at time 15 seconds. So when I take a look at that, I would need to calculate the concentration by saying the concentration at time 15 seconds will be the number of moles of oxygen produced. This is coming from the problem, over the volume of its container. And it was in a ½ liter reaction vessel. So I put that together, I end up with 0.030 molarity. So this is the molarity at time 15 seconds. Now, the way that I can find the rate, because this is a change, delta means change, okay, I'm looking at the final minus the initial for the top and the bottom. Okay, so rate here is going to be equal to the change in concentration over the change in time. So the change in concentration, the final concentration was 0.030 molarity minus 0 molarity. And the change in time was 15 seconds minus 0 seconds. And so if I solve for that, I'm going to find that the value is 0.0020 molarity per second. So keep in mind your units here, molarity per second. That's a rate. Okay, so you could also have written this, which is perfectly fine, as 2.0 times 10 to the -3rd molarity per second, whatever your preference is. But this would be the correct answer for B here. All right, let me just delete some of the cell potential work here to make space for C. All right, so for C, we're going to have to use a combination of A and B in order to obtain the value we'd like for C. So the first thing we do comes from A. We want to set up the relationship and say, how does the disappearance of N2O relate to the appearance of the oxygen gas? And we can do that from A by saying, I know how these two relate to one another. It's this equals this. So that's what we're going to rewrite down there. Okay, so this is for C. It's going to be -1/2 delta N2O over delta T, okay, is equal to delta O2 over delta T. Now we have already solved for this value right here. So what we're going to do is set this value equal to -1/2 delta N2O over delta T, get rid of the -1/2 because we're going to apply that over to the actual numerical side, and then we will find the value for this right here, and that will be the rate of disappearance for that. All right? Now keep in mind, this should be a negative value. There's a -1/2 that is set up into this. So when that negative gets flipped to a reciprocal -2 and multiplied, then you're going to get a rate that's negative. That simply means it's disappearing. It's talking about the direction. Okay, so what I need to do then is say delta N2O over delta T is going to be equal to, now again, -2. I'm going to multiply this here in order to get rid of it. So -2, I have to do the same thing to each side. You going to stay quiet? Okay, so right here, we have this value. This value is going to be 0.0020 molarity per second times -2. And if you take that value, you're going to end up with the rate for the disappearance of the reactant, and it would come out to be -0.0040 molarity per second. All right, so again, this is a combination of A and B. A sets the relationship up, B solves for one of the rates, and then if I have one of the rates, I can relate it to all of the others based on the relationship they share in part A. So it would be completely possible to also solve for the appearance of nitrogen gas. Even though this question did not ask you to do that, all you would have to do is the same technique we did in C. Instead of -1/2 here, you would have a +1/2, and this would not be delta N2O over delta T. It would be delta N2 over delta T. And then you would simply multiply by a +2. And so the appearance of the nitrogen gas would be the same exact value, but it wouldn't be negative. It would be positive. Okay, so I'm going to stop here because that concludes 6, and 7 is the last one that we have to get through. So are there any questions regarding this? All right, so initial steps, let's find how everything relates to one another through variables. Then take what's known, find one of those variables, and then you can solve for any of the other variables once you know that individual variable. All right, so number 7 might seem complex because there's a lot of wording and there's multiple things that you need to solve. But this is actually one of the easier problems. I would argue it's probably close to the easiest problem of the bunch if you know what you're doing. All right, so let's talk about this here for a second. A reaction is known to react with A, B, and C together in order to yield several products. So that means I have 3 reactants. They're called A, B, and C. Now, experimental data has determined that A is going to be first order, B is going to be second order, and C is going to be 0th order. So knowing this, it wants the following. Write out the rate law for the reaction. What is the overall order for the reaction? And then C, D, and E are all saying the same thing. They're saying if you manipulate and double the concentration of a specific reactant while holding everything else constant, what would you expect to happen to the rate based on this? So we're going to go through and logically walk through this. And I think you're going to see there's very little math that needs to be worked out in order to do this. Now, there are certainly math-heavy versions where they're giving you specific numbers, but this is a general method here. All right, so I think we got enough space here. So let's talk about it. First of all, you have to understand what order is when we're talking about this. So anytime it refers to order, it's talking about the exponent that the given concentration will be raised to. So if I say something is first order in a reaction kinetic scheme, I'm saying this. If I'm saying something is considered second order in a reaction kinetic scheme, it's this. Okay? If something is to the 0th order in a reaction, it is this. Okay? And that means that when something is to the 0th power, it becomes 1. So no matter what I put in here, I'm always going to get 1 back. Okay? Whereas these others, it could vary. And you could have third or fourth or anything like that as you continue the exponents. So for A, if you understand what order means, it says give the rate law. So the rate law is going to be the rate equals, we have to remember that we have a small k, that's our rate constant. And then if you look at what it said A is to the first order. So it would be A is to the first order. B is to the second order, and C is to the 0th order. All right. So if you keep in mind what's going on here, when A is raised to the first order, that means whatever is inside of A is what's going to exist there. So I can drop this value because that'll be implied. And if C is to the 0th order, that means that this value will always become 1. And anything times 1 is itself. So I can drop this whole material out of here. So the way that I can write this is I can say that the rate is going to be equal to the rate constant times the concentration of A times the concentration of B squared. That's the correct way to write the rate law. All right, now I would give you the bulk of your credit if you wrote this first one that's over on the left here. However, you're giving redundant information that doesn't need to be there. It's like stating something is multiplied by 1. It's the same thing when you have a 1 for your exponent up here. That's like putting a 1 in front of your balanced reactions. It's implied. The very fact that it's there means you have one of it. Okay, so this would be the correct rate law. Now, the second question says, what is the overall rate of the reaction in terms of its order? So it wants to know the overall order of the reaction. Well, the only thing you need to do is take a look at the individual orders and put them together. So when we have exponents and we are multiplying, it means we add the exponents together. So if I look at the rate here, I've got an implied 1 and I have a 2. So I just add them together and I get a 3. 1 plus 2 is 3. So that means this is going to be a third order reaction. All right. So C asks, if you double the concentration of A and you hold everything else constant, B and C, what is going to happen to the rate? So let's take a look at that. Here's the rate law. If K is a constant, right, it's the rate law constant, and B is being held steady and C is being held steady, what's going to happen to the rate of the reaction if I double A? It's going to double. Okay. So if everything is held constant and then I take something and I multiply it by 2, then I expect the rate is going to be multiplied by 2. So it's going to be a rate times 2. That's all you had to put for that. Now for D, it wants to know the same thing for B. So now I'm doubling the value of B and I'm holding K, A, and C constant. So what's going to happen there? Now I'm going to have a rate times 4. Now why is that the case? Because if I take a look at rate, right, and I hold everything constant, so we'll just put a 1 in place of anything constant. So that's 1 and that's 1. And then here, instead of it being 1 squared, I put 2 squared. That's 4. So that means that the rate is going to jump up by 4, right? Because if this was all 1, 1, 1, 1, then I would expect the rate is 1. And then if I suddenly say I'm going to double B while holding the others constant, then it's going to become 1, 1, 4 because of that squared value. And so I would expect a quadrupling in the rate, okay? So what that means is that the rate is more dependent on B than it is A. It's dependent on both of them, but as I change around B, I'm going to see more drastic changes in the rate of the reaction in comparison to A. All right, now E wants you to do it with C. So it says now you're going to change the concentration of C and you're going to hold the others constant. So what's going to happen in a case like that? Well, C is raised to the 0th power, meaning it's completely absent here. It doesn't even affect the rate, right? If it doesn't appear in the proper rate law, then it can't affect the rate. So I could double it, quadruple it. I could send the concentrations all the way up to the moon, and nothing's going to happen as far as the rate. It's going to hold steady because C does not have any influence on the rate. So this means if I wanted to put something here, it's going to mean that the rate will be unchanged. There's not going to be any effect on the rate given that. Okay, and then for the finale, it says, what happens if you no longer hold constant and you attempt to double everything? Well, all I have to do is take a look here. If I double C, I get a doubling of the rate. If I take a look at B, I quadruple the rate. And if I take a look at C, I end up doing nothing to the rate. So 2 times 4 is 8. So I would expect an 8-fold concentration in the rate if I was allowed to double everything that was present. And that is the correct answer for F. And that brings us to the finale for the worksheet. So I'm going to pause here. Are there any questions regarding this problem and understanding order, understanding how order is going to play into rate or affect rate?
Can we expect to see something similar to this on the quiz on Monday?
Not exactly like this, but yes, you can expect that you're going to have to understand order. It is a very, very good multiple choice question for me to turn around and say, here's a rate or a rate law, and give you something like I have squared right up here and say, given this rate law, what would you expect happens if I double the concentration of B to the rate? And then I could have a bunch of different answers. Now I could also ask you, tell me what's going to happen. But these make very, very good multiple choice or true false questions. So I would expect it to see it in that sort of format. Okay, now again, this is a very generic form. So I could start also giving values, right? And I could say, B is increased from 0.2 molarity to 0.33 molarity. What is the new rate? And then you have to be able to plug it into the rate law, execute with the proper values. Now you would need to know the value of A at that point, but you should be able to see what's happening to the rate given the rate law. So these laws govern how quickly the reaction goes, and you can change any of the concentrations and the law will return the rate to you based on that change. Okay, any other questions? All right, so what I'm going to do then, I'll go ahead and stop share, and I will also stop recording so that